Fatigue failure is the Achilles heel in parts produced by laser powdered bed fusion, where surface morphology plays a more dominant role than bulk material properties themselves. My name is Papamalama, and today I will show you how hardization turns that surface into strength advantage. My work is focused into enhancing surface quality and fatigue resistance of sub-millimeter laser powdered bed fusion aluminum lattice structures via hardization. The motivation behind the work is that surface roughness can be considered as a defect, further deteriorating fatigue properties. And sinter particles inherent to the laser powdered bed fusion manufacturing process can act as fatigue crack initiators, directly reducing fatigue lifetime. And because lattice structures display this high surface to volume ratio, this effect is even more pronounced. And here comes the knowledge gap. Can hardization really enhance fatigue performance? And by hardization, we mean a hybrid chemical, electrochemical surface process treatment, mainly consisting out of 3 steps: the dissolution of sinter particles and supports, the cleaning of the surface, and the final polishing of the surface. For the architecture and the material, I have worked with aluminum A205. You can see the composition of the alloy on the screen. My main geometry was a rhombic dodecahedron unit cell of 2 millimeters, stacked horizontally and vertically 7 times to produce a cube with outer dimensions of 14 millimeters edge. The relative lattice densities, the nominal ones manufactured in this way, were 10, 20, and 30% relative density, as you can see here. And the upper parts are the diameters in micrometers for each category. And the main categories for comparison were the S-build on top and the hardization treated on the bottom. Now, regarding hardization and enhancing surface quality, from the entire spectrum of surface roughness parameters, I chose to show you the average surface roughness on the left and the skewness on the right. And what we can observe here is, for instance, the blue is for the relative lattice density 10% before and after the treatment, sitting next to each other, side by side. The orange one is for the relative lattice density 20%, and the gray is for the relative lattice density 30%, as shown by the legend. So what we can observe is that, indeed, the interquartile ranges, minimum, maximum, and outliers have been thoroughly reduced. Now, regarding on the right the skewness, we can observe a surface morphology change from peak-dominated to valley-dominated, as we can see from the change from positive numbers to negative numbers over here. Now, this slide shows the average surface roughness reduction expressed as a percentage in those bar plots. And we can see that for the 3 categories of relative lattice densities, we have a span of surface roughness reduction from 23 to 48%, with a maximum, the 48%, almost touching 50%, occurring at the relative lattice density 20%. For the quadratic tests, I have applied a compressive load on the -z direction opposite to the build direction. And what we can see here from the diagram, the dashed lines are the hardization treated, and the solid lines are the S-build as manufactured. So we can see a gradual transition from a bending-dominated behavior to a stretch-dominated behavior with increasing relative lattice density, which is consistent to other researchers' work as well. For the fatigue tests, I have applied a compressive load, compression-compression ratio, equal to 10. And I have also observed a fatigue life extension. And here's the explanation. On the y-axis, I have the amplitude stress divided by the yield stress of each category for the sake of normalization. On the x-axis, we can observe the lifetime in cycles. The solid markers are the S-build, and the hollow markers are the hardization treated. So we can see that for the same stress ratio, we can observe a thorough increase in the fatigue lifetime. Or if we think the other way around, for the same lifetime, the hardization treated samples can take up more load. This slide shows the fatigue improvement after hardization expressed again as a percentage for the 3 different relative lattice densities categories. And we can see that we have a spanning from around 5 to 35% increase in the fatigue lifetime, with a maximum of 35% occurring for the relative lattice density 10%. Now, how is this achieved? We can see here, what we see here is a cross-section of the top view of the lattice structure in the S-build state from micro-CT. And if you observe closely, you will see a lot of semi-fused particles attached throughout the struts in the entire lattice structure. On the other hand, after the hardization, we can see that those semi-fused particles have been successfully removed throughout the entire lattice structure, thus promoting a more uniform surface and a more uniform load distribution throughout the structure. For the fractography study, consistent to the theory, we can observe distinctive failure planes at around 45 degrees, both for the S-build, which are on top, and for the hardization treated. The free boundaries of the lattice structure, which is a cube, act as crack initiators. As you can see here, we have more extensive damage on the outside, and then the cracks progressively make their way inside the structure. We observe macro strut detachment, as you can see here, and the failure happens at the nodes or close to the nodes. This is where maximum bending moments are created according to the beam theory, and this is also where we have a lot of geometry changes due to the waviness, the change in diameter within the struts. Crash bands are formed both in the S-build and the hardization treated category, and there is this observation of a hybrid brittle to ductile failure mode. This is more observable here, over here. On top, we can see a more ductile way with a darker surface, more plasticity occurring, the dimple cycle after cycle. While on the bottom, we can see a more clear surface fracture, resembling to the cleavage from the theory of the materials, thus strongly indicating a more brittle failure mode. For the conclusions, we can think of the analogy of the materials tetrahedron, where structure, properties, and processing act synergistically together to enhance the final performance of the material. And in this case, we can think of the processing being the hardization, and the final goal that was achieved was the increase in the fatigue lifetime. So the main highlights and takeaways to take home is that indeed, hardization is an effective post-processing route, enhancing fatigue life and surface consistency, making suitable to adapt into lattice structures designed for lightweight applications. Hardization, indeed, has reduced surface roughness and removed attached particles, enhancing surface condition. And because lattice structures have this high surface to volume ratio, this reduced stress concentration, thus promoting a more uniform load distribution, thus delaying crack initiation, and ultimately increasing fatigue resistance. The paper that supports those findings is this one, comparing geometry and mechanical performance of S-build and hardization-treated H2O5 rhombic dodecahedron lattices manufactured by laser powder bed fusion. My PhD topic within the Metamath doctoral project is the production of fine metamaterial features in metal by laser powder bed fusion. Grazie di cuore per la vostra attenzione.